This PowerPoint is going to be over angular or rotational momentum. All right, so the momentum of a rotation is going to be the rotating mass having an angular velocity, and it has an angular momentum if it has an angular. So the mass itself, the moment of inertia, times the angular velocity is going to give you the momentum of an object. But for an object that's moving in a straight line, that has linear momentum, it's mass times velocity. So if you look at the angular momentum equation, it looks very similar. The angular momentum, which is a capital L, is a moment of inertia, which is basically the mass of an object that's rotating, because the mass or the inertia of an object that's rotating is not just its mass, but it's also a distribution, the k value and the r squared. And then just like with linear momentum, it has a velocity. With angular momentum, it's going to be angular velocity. So the moment of inertia times angular velocity is going to be equal to the angular momentum of an object. All right, so let's talk about a rod, a 3 kilogram rod of length 0.6 meters. It's rotating at the center with an angular velocity of 5 radians per second. So what's the moment of inertia? Well, the moment of inertia of a rod around its center, the k value, so that k value times mass times radius squared, so it's going to be 1/12 times 3 times 0.6 squared, and we get the moment of inertia as 0.09 kilograms meters squared. So now we look at the angular momentum. We take that moment of inertia, multiply by the angular velocity, we get 0.09 times 5, and that gives us 0.45 kilograms meters squared per second. Now, some weird units there, but they don't change to anything else. Like kilogram meter per second squared converts over to newtons, but kilograms meter squared per second for angular momentum just stays as it is. This example, now we're going to do the same thing, except we're going to rotate it around its end, which means the k value is going to change. So it still has the same angular velocity, it still has the same mass, same length, but we just changed the axis of rotation. So the axis of rotation now being at the end, that makes the k value going to be 1/3. So 1/3 times 3 times 0.6 squared, that gives us 0.36 kilograms meters squared. Now, since the moment of inertia changed, that means the angular momentum is going to change. We take that 0.36 times 5, we get 1.80 kilograms meters squared per second. Now, with an increase in angular momentum, or I'm sorry, an increase in moment of inertia gives us an increase in angular momentum. All right, so what is the angular momentum of the Earth as it's rotating on the axis? So we're just talking about the Earth as it's spinning in place. What is its moment of inertia, and then what's going to be its angular momentum? All right, so first off, a k value of the Earth we're going to assume is 2/5. We're just assuming it's a solid sphere. It's really not. It's not an equal density all the way through, but just for the simplicity of this problem, we'll say it's 2/5. All right, so 1/2 times the mass. So 1/2, I'm sorry, the k value, which is 2/5, k value times the mass of the Earth, which is 6 times 10 to the 24th, times the radius of the Earth, which is 6.4 times 10 to the 6th. We're going to square that. We go ahead and multiply that through. We get the moment of inertia of the Earth is going to be 9.8 times 10 to the 37th kilograms meters squared. All right, so now that we have the moment of inertia, let's look at the angular velocity. Now, angular velocity may not know how to find the angular velocity of the Earth, but if you think about it, angular velocity is related to period. Period of the Earth is a little bit less than 24 hours because one day, a 24-hour period, is actually a slightly more than one rotation of the Earth. So the moment of, the angular velocity is going to be equal to one revolution divided by 23.9 hours. Remember, the angular velocity is actually radians per second. So one revolution for the Earth is going to be 23.9 hours. Let's go ahead and convert that. We get 1 hour is 3,600 seconds, so that gets us seconds in the denominator. The revolutions, it's going to be 2 pi radians equal 1 revolution, so we cancel out the revolutions there. Then we go ahead and multiply everything in the numerator, divide by everything in the denominator. We get 7.3 times 10 to the negative 5th radians per second. So now we have the moment of inertia and angular velocity. So let's go ahead and multiply these two together to figure out what the angular momentum is for the Earth. And you get 9.8 times 10 to the 37 times 7.3 times 10 to the negative 5th, and you get the angular momentum of the Earth as it's spinning on its axis is going to be 7.18 or 7.15 times 10 to the 33rd kilograms meters squared per second. Next problem, let's say we have a point mass that is going in a circle. So what's the angular momentum? Remember, the k value for a point mass is going to be 1. So as this object orbits around in a circle, what's going to be its angular momentum? Now there's actually a little bit, there are two ways to actually consider this. Since this is a point mass, you can actually talk about its mass and velocity and talk about its momentum there, and then translate that over to angular momentum. We'll get to that in a second. But for a point mass, its K value being 1, let's go ahead and find its moment of inertia. That's going to be 1 times mass times radius squared. So then we plug that in for the moment of inertia. We get mass times radius squared times the angular velocity. And then the angular velocity is going to be equal to the velocity divided by radius. So we go ahead and plug that in there. And what we get is we get mass times radius squared times velocity divided by radius. We cancel one of those radii. And what you'll notice is mass times radius times velocity. Now, if you take the mass and the velocity, that is momentum. So for a point mass, we can actually take the object's momentum and multiply by the lever arm. The lever arm refers to the distance from the pivot point, the axis of rotation, to the line that goes through the momentum, which is the same as the line that goes through the velocity. So just like in torque, if we have a force times a lever arm, that we take a line, draw a line through that force, and the closest distance from the force to the axis of rotation is the lever arm. Now in these examples, we're going to be dealing basically with an object moving in a complete circle. In that circle, the radius is going to be constant the whole time, so the lever arm is going to be equal to the radius. But it can get more complex that if you are doing an ellipse, for example, then the lever arm is actually going to be changing according to what angle it is with the momentum. All right, so let's take this 0.5 kilogram ball that's rolling around in a circle with a radius of 0.1 meters, and it has a speed of 1.4 meters per second. So what's the angular momentum of the ball? Okay, so we can take its actual momentum, which is mass times the speed, or we can use this equation where we find its angular momentum by taking the moment of inertia times the angular velocity. So the K value for a point mass is going to be 1 times 0.5 times 0.1 squared. That gives us the moment of inertia 0.005 kilograms meters squared. Then we could use that with the angular velocity. So the velocity, which is going to be 1.4 divided by 1, or 0.1, that gives us 14 radians per second. Moment of inertia times angular velocity, that gives us 0.005 times 14, and we get the angular momentum is 0.07 kilograms meters squared per second. Okay, so that's using the strict definition of what we usually use for angular momentum, and that's just the moment of inertia times angular velocity. Now, let's use the equation we just solved for the point mass to show that we should be getting the same thing. So we have the mass times velocity times radius, all right? So mass times velocity is, again, that's the momentum multiplied by the radius, so 0.5 times 1.4 times 0.1. Multiply all that together, you get 0.07 kilograms meters squared per second. So you can see that regardless of which equation that we use for the point mass, we'll get the same answer either way. So effectively, we can just use whichever is convenient based on the information given to us. Now in the problem, it told us the mass, it told us the speed, and it told us the radius. So it would have been a lot easier just to do this point mass equation as opposed to finding the angular momentum with the moment of inertia times angular velocity. In this example, it says just like in linear momentum, angular momentum also is conserved with no outside net torque. So as long as we don't have anything on the outside applying a force causing it to either increase or decrease its rotation, with no outside net torque, momentum, angular momentum specifically, will be conserved. So if you think about something that's spinning in a chair, and this is an example I do in class, and you can actually see this example a lot with people who are spinning around in a chair, and they'll have masses in their hands. Now, as they move their masses away, as they move it away from their body, that actually increases the K value. It increases the radius, which increases the moment of inertia. And if you increase moment of inertia, but angular velocity is constant, then that means it'll decrease the angular velocity. Likewise, if you take your masses that are out really far and pull them in, then what that does is that decreases your moment of inertia, which will increase your angular velocity. Now, what's interesting about this is a figure skater can do this naturally. And what they do is before they start going into a spin, they'll actually hold their arms out really wide, and then they'll start spinning and then pull their arms in. Once they pull their arms in, they decrease their moment of inertia, which makes them spin faster. And if they're up in the air doing a spin, right before they land, they'll throw their arms out again. And when they throw their arms out, that'll slow their spin down so they're more able to land. So that's a decrease and increase of moment of inertia, which increases or decreases the angular velocity because the angular momentum is going to be conserved. All right, so in this example, it says a child that is 24 kilograms spinning in a merry-go-round that has a mass of 88 kilograms. Merry-go-round can be thought of as a solid disc with a radius of 3 meters, and the child is standing 2 meters from its center. Okay, so what's the moment of inertia of the merry-go-round and child system? Since we have two objects, we can essentially take the moment of inertia of each object, figure out what they are individually, and the total moment of inertia is literally going to be those two added together. So let's go ahead and take the child, which is going to be the mass of the child times its distance from the axis of rotation squared. And then the moment of inertia of the merry-go-round is going to be 1/2 because it's a disk. Solid disk has a K value of 1/2 times mass of the merry-go-round times its radius squared. We'll go ahead and plug those numbers in. The child is 24 kilograms times 2 squared plus 1/2 times 88 times 3 squared. That's the merry-go-round. We get a total moment of inertia of 492 kilograms times meters squared. Now, if the merry-go-round and child system has an angular velocity of 2.5 radians per second, what's the angular momentum? Simply put, we take the moment of inertia times the angular velocity, and that gives us 1,230 kilograms meters squared per second. So in this part, we say, well, what if the child moves? All right, so the radius of the merry-go-round is 3 meters, but the child is standing 2 meters from the center. So what if the child goes to the edge? Well, think about what happens to the moment of inertia. If the child goes to the edge, they're increasing their radius, which means they are increasing their moment of inertia. So what we'd expect is we expect the moment of inertia to increase, but since we're talking about the force between the child and the merry-go-round, the force of friction between them, that's an internal force. That's not an external torque. So the angular momentum will be constant. As the child moves out, then the angular momentum will be constant, but the moment of inertia will be changing, which means the angular velocity would change. So that brings us to the question, what's going to be the new angular velocity of the system? All right, so now we're going to find the new moment of inertia. So the new moment of inertia is going to be the mass times the radius, which is going to be 3 this time squared. All right, so that's what changes, and everything else stays the same because the moment of inertia of the merry-go-round stays the same. The mass of the child stays the same, but we go from 2 to 3. So we go ahead and multiply that through. We get 612 kilograms meters squared. As you can see, the moment of inertia has increased. So we got our moment of inertia before, our moment of inertia after, but the angular momentum is going to stay the same. So let's start plugging this in. We got the initial angular momentum is going to be equal to the final angular momentum. So that is the angular momentum initially was 1230. So we plug that in. That's going to be equal to our new moment of inertia times angular velocity. So the 612 times the final angular velocity the second time. So we divide both sides by 612, and we get our new angular velocity is going to be 2 radians per second. Now recognize that initially we had an angular velocity of 2.5. That's how we found the moment of inertia, and the moment of inertia times the angular velocity found the angular momentum initially. All right, so with an increase in angular momentum, we decreased our angular velocity, and that's because the angular momentum is going to be constant either way. So in this example, we saw that with the merry-go-round with a child, as the moment of inertia increases, the angular velocity decreases because the angular momentum is conserved with no outside net torque. But what about kinetic energy, rotational kinetic energy? Is rotational kinetic energy also conserved? Well, if you look at the equation itself, we got moment of inertia times angular velocity. That's going to be conserved. But then kinetic energy is moment of inertia times angular velocity squared. So if I have half the moment of inertia and I double my angular velocity, then that means I'm going to have 2 times 2 squared, or 1/2 times 2 squared, which is going to be 1/2 times 4. So I'm going to have twice the rotational kinetic energy. So rotational kinetic energy is actually not going to be conserved in this instance. So why not? Why not? What does happen? In order for there to be a change in rotational kinetic energy, there has to be work that's done. But we already said there's no outside net force. So how is that possible? How is it possible to change the kinetic energy? All right, well, the work being done is actually going to be caused because as the child moves out from the center, the direction of the force is towards the center because it's a centripetal force. An object moving in a circle has a centripetal force, and the force is always towards the center of the circle. So as the person or as the child moves towards the center of the circle, then that means the force is towards the center, the displacement is towards the center. So the work that's going to be done on the child is going to increase the rotational kinetic energy. So as the mass gets distributed more towards the center of the circle, we actually have an increase in rotational kinetic energy. Now, what if the child moves outward? If the child moves outward, then the force is still going to be towards the center because you're still moving in a circle. Think about what would happen if you let an object go. If you let it go, it would move out and away from you. Technically, it'd move perpendicular from where it was let go from, but that would move away from the center. So even if you're still holding on to the mass and the person spinning in the chair, for example, if they were to move outward, there's still an inward force on those objects keeping it moving in a circle. So even though the child that is starting 2 meters out from the center going to 3 meters out, if the child wasn't on the merry-go-round at all, they would move away from the merry-go-round. So it's still a center-seeking force, but the displacement is outward. So as the mass moves outward, then that means the work done is going to be negative. You're going to have a negative change in rotational kinetic energy.